In this part, we are going to discuss the details of lists and tuples. Both lists and tuples can contain mixed type of elements. They might be primitive types such as strings, integers, floating point numbers, Boolean values, as well as they might contain complex types such as other lists or tuples. In order to find out which type an element is inside a tuple or a list, we can iterate over those items and check the type of each individual item, each individual element, for instance, using the in operator on our list, or it might be a tuple. We can iterate over each item one by one and print the type of that item using the type function. So if you want to know what type of that item is, you can simply use this function, and it's going to return a string in this form, such as the class is str, for instance. So you can use this information to do other things. You can parse this string, this output string, and convert from one type to another type if it's necessary based on this information. You would need to write other code for it, but if you are interested in finding out the type of the item in a container, you can simply use this type function in your code. One important thing that we're going to be discussing in this section is that primitive types are referenced or copied by value, but complex types are referenced by address in their memory. For instance, when you define a Boolean value, let's say it contains the value false. If you want to assign this value to another variable, let's say my bool is currently false, okay, assign the value false. And if you want to assign this value to another, my other bool equals my bool. My other bool is currently containing the same value as my bool, but at a different location in memory. So when you change the value of my bool, my other bool is not going to be affected from this modification. So because they are pointing, they are stored at different locations. We can experiment this very quickly in this code, in the sample code. So my bool, let's make it false, and let's assign my other bool to have the same value as my bool variable, and let me modify my bool variable to be true. And if I print the value contained in my other bool, I'm going to encounter a false, which was the initial value assigned to my bool, because primitive types work as copy or pass by value principle. But complex types do not work in that principle. They are reserved a space in the memory area. So I have this list of mixed items containing red 2.3 for true and a pointer to a list in the memory. So this list is preserved at another location in the memory, there's a reference to that list. The list contains another list. Okay, the strings contained in the lists are another and the list. So there's a pointer to this sub list or inner list in my memory. When I want to assign this, we're going to see that copy operations and application or removal operations. We're going to discuss this as well. This reference is also passed on to the copy of this list if you make a copy from this initial list. So if you modify this internal list, it's going to be reflected to the other copy as well, because they are both going to be pointing to the same location. However, if you modify one of the primitive types in this list, such as replacing red with yellow or replacing it, removing it from the list, this is not going to be reflected to the other copy. So these are two differences between pass by value and pass by reference operations. You should be careful when you are making operations on complex types. They are going to be reserved in the memory, and all other references are going to point to the same location unless you specifically make a copy or duplication of that sequence of items. You just know that there are lists of lists, so every internal list contained in another list are stored at different locations in your memory area, and they are all going to be passed by reference rather than passed by value. So whenever you have such a list being pointed by another variable or another container, there's only going to be one copy of that item, of that container, of that internal container, let's say, or sub container. If you need copies to be preserved, if you don't want them to be modified, you should make explicit copies somewhere else in the memory, pointed by a controlled variable. So we have this example here for you that we incrementally modify the values, such as there are three variables, color, number, and boolean, all set the initial values yellow, 10, and true respectively, and we have a sublist which are all assigned to a tuple initially. Although the tuples cannot be modified, their internal items can be altered if they are complex types. So if you want to remove color from your tuple, this is not going to be allowed. You cannot assign something else because these are all primitive types, but you can change the items in your sublist. This is allowed because the tuple itself is a definition that contains the current color value, which is yellow, not the variable itself. It's pointing to the value contained inside that variable. Okay, it's just copying them or passing them by value. So this is what is contained in your tuple in the memory, and there's a reference to your list which is at some other location in the memory. So this sublist is in fact here, stored here. It contains 123 and 213. This is the sublist. However, when you modify the value of color, which was yellow initially, to red, Now this color variable is pointing to some other string. It's not pointing to the yellow which was initially placed into your tuple when you were constructing it. So this is not going to modify your tuple. Similarly, number is not going to modify this tuple, and this converting the Boolean variable to false is not going to affect your tuple. However, when you replace the first element in your sublist, it's going to be reflected to this output because it is not actually stored in your tuple. It's pointing to some other location in the memory. So it doesn't violate the definition or the rules of tuples. It is still pointing to the same list in the memory. But when you modify the contents of that other list, when you output this list along with the tuple itself, it's going to reflect the modifications to your output. This is another important fact about pass-by value and pass-by reference. You can also add items to the back of the list using the append command, append function, append method. And when we run this code, we can clearly see that our tuple is not modified when we are talking about the primitive types. Okay, so the code goes yellow 10 true, assign them to the tuple, modify those variables, and also modify the sublist, which is passed by reference, passed by address, memory address. And when you try to print each item in your tuple, it contains the initial values for the primitive types, and it keeps reference to the sublist, which is modified after the initialization. Okay, the sublist here, the sublist is here, assigned as a reference to the tuple, and it has been modified before we retrieve the items in the tuple. So we see this list has been modified. The first element has been converted to 34 instead of 123, and 54 is appended to the list, so it becomes 34, 2, 13, and 54 instead of 123 and 213. So we see the effect immediately reflected to our tuple, but the change did not occur in the tuple itself. It happened in a list which is passed by reference, and a pointer is kept inside the tuple for that list, so it doesn't violate the rules and definitions of the tuple. And we also have this second list, which contains color and number as its components. For instance, color has the value red currently, so the last value assigned to the color is red. When I construct a list using the square brackets, I enter red and 11 as the items, list items. Although I modified the color variable to blue, it is not reflected to my list because it is using these values, using these variables as pass-by value, making a copy of those items. In fact, what happens is, you know from strings that when you define a string red, this is stored at some location in the memory. Every variable every reference to the same sequence of letters that constitute red are going to be pointing to the same location in the memory. So there is never going to be a copy of red in your memory. You're not going to see another red in memory during your program's execution. So this memory area is specific or dedicated to your program. There might be other programs that contain red. Okay, these are distinct memory areas, but in your program you're going to have only one entry for red, and every variable independent from each other, let's say color1 equals red, color2 equals red, they are all independent from each other. You could have written something like this: color3 equals color1. Okay, they are still independent from each other, primitive variables. So they are all going to be pointing to the same location in memory. Once created, once mentioned in your program, it is placed in somewhere unique in the program memory, and every other reference to the same string are going to be referencing to the same address. Similarly, in this list here, when we assign color to our list, this list is going to be referencing to the same location because it is using the value stored in your variable, and then that value is unique and stored in somewhere. It's the same for the number 11. 11 is stored at some location in the memory, and there's not going to be a copy of that, no matter how many times you assign them as variables. Okay, same thing happens here. So if you modify the value of your color variable, it's now going to be pointing to some other location, blue. Okay, this color is now pointing to blue, which is at another location. However, my list is still pointing to red, as it is a primitive type, and pass by value operation holds in this case, no matter how many times you change your primitive variables. We can unpack the elements inside a tuple or a list to multiple variables, as in this example. We first define a tuple containing some information about a student or a person. Okay, there is an age field, name of the student, occupation of the student, let's say undergrad, or type of the student, undergrad student, number, interests or courses of that student, and there's an email address at the end of this tuple. We can unpack them by assigning each and every data contained in this tuple age. So this is how it's going to behave. Age is going to be assigned to this first variable. Name is going to be assigned to the second. Occupation or student type may be assigned to the third one. ID or the student number. And now I don't have 4 more variables, and I'm not interested in those details. I'm only interested in 4 of these. I can simply use this asterisk symbol before this other info variable. Okay, I lost my keyboard again. If I use this asterisk symbol, it's going to unpack all the remaining data after the ID field. as a list to this other info variable. So when we output this, when we run this code, we're going to see that reading math student address and email address goes into this other info field because we want them to be unpacked as a list. We might not know how many items are going to arrive that are going to be unpacked, but we might be sure that first 4 of them are going to be age, name, occupation, and ID. So if this was in a function that we received information about people and we were certain that only the first 4 are well known and the remaining ones might be 4, 5, 15, 100 different items. We can all unpack them to the other info field using the asterisk symbol as a list. You can also do something like this after this asterisk symbol. If you are certain that the last entity in your tuple or collection is going to be the email, you can add this as well. So now the unpacking operation is going to happen as, because we assign it using the assignment operator. So the age goes to the first, ID goes to the fourth. Now we encounter this one, and there's something else after the asterisk variable. We know that there's an email on a single entry, so we use the last one as the email and take all these in between, assign them to the other info. Now that we can see print email, now that we can see that it doesn't contain the email address in the other info field, but a dedicated email assignment has taken place. And if I want to assign the student address as well, st address, now it's going to assign them one by one. ID, now I see this special variable. I stop there. I don't know how many I have to skip. So I move to the end of the list, assign this one, email, and then assign the student address. Okay, now I have 2 left out of the list. So I can see clearly that all the assignments have taken place correctly. I have the email field, and before the email field, I can output my address field, student address, or in any other order. You can output them in any other order. Okay, let's say you have the name before the age. The unpacking order is determined by this assignment operation. So this operation determines which item is going to go into which variable when you are assigning them. We don't actually know what's going to happen until all dedicated variables are unpacked and the remaining ones are assigned to this one. There could be other information in this reading maths, whatever lecture you have. Let's say you have chemistry class. Okay, you can have as many items as you need. Okay, physics, but the operation is going to take place in the same way, such as assigning all these one by one until you encounter the special variable, and then you go to the end of the list, assign them one by one starting from the end, and the others left out are going to be unpacked as a list to the other info, the special variable. If you run this code, you're going to see that now other info contains 4 items instead of 2. This is a very special use of lists and tuples, that you can obtain multiple variables. You can assign multiple variables out of a tuple or a list. But if you skip this asterisk operator, you're going to receive an error because you have 7 variables specified. However, you have more than 7 items that can be unpacked in your tuple, but there are only 7 specified. If you do this like this, it's going to cause an error in your program. So it might be a wise move to use the special notation, so that if you are only interested in 4 of these items in the beginning or at the end, this might be your case as well, you might simply discard the first all items that appear before the student address and email, which you know are going to be placed as the last elements in your tuple. The slicing operator can be applied to lists and tuples as it can to strings. For instance, we have this example list from which we want to obtain the values 5 and 6, 5, 6 and 7. So it's going to output 2, 3 and 4 up to 5, but we don't have a 5th element. It starts with 0, goes with 1, 2, 3 and 4. The length of this list is 5. So we specify the upper bound to be the largest value up to which we are going to retrieve the items from the list or tuple, but it's not going to include the upper bound as an index. So if we open this example, first let's take this out. So this is the second recording I made in this chapter, because the one I recorded was in there was an audio problem, so I have already modified these examples. So the first part simply outputs the elements, the items between index 2 and 5, including 2, excluding 5. There's a sublist. And the second example is, by the way, you can use negative indexing in your lists and tuples. It's going to simply subtract the negative index from the length of that container, which is the temp variable. List name is temp, or it might be a container, whatever, my list, your list, the other list, color list, whatever you call it. It's going to simply subtract the index, which is a negative, if it's a negative value, from the length, and find out what you are referring to. It's a powerful feature for Python, but it saves you the trouble from and it saves the trouble from subtracting length of the the value from the length of the container each time you need to access it from the end of the list. So you can use it in that way. But you shouldn't exceed the beginning of the container. So you shouldn't specify something less than the negative version of the length of your list. So it shouldn't be exceeding your list boundary on the lower index, if you know what I mean. And in the second example, we have our list being modified. Let me run it first for you. So we have this list 1, 3, 5, 6, 7. We modify the second item in our list to be 13, and we use a slicing operator to replace a part of our list with a new list. So there are two items to be modified, 2 and 3. These are the indices. So at index 2 we are going to assign 15. Index 3 we are going to assign 16. And its output is that I have individually modified this location 1, and I have modified these location 2 and 3 at the same time using a list or slicing assignment with a slicing operator. You can also assign multiple values that are larger than the slicing area. So if you do that, as in this example, I am specifying the same location as in the earlier example, only 2 and 3 are going to be modified, but now I have 3 elements that are going to be modifying this area. What happens is it moves or replaces 15, 5 with 15, 6 with 16, and it inserts 17 after 16 and shifts this 7 to the right. When we run this code, you can clearly see that the list has been expanded from inside out. So it doesn't touch these one. We didn't modify the first element in this case. We simply modified 5 and 6 and inserted 17 right before 7, and it shifted 7 to the end of the list. So there is a larger part that is going into the list, replacing those ones that are at the boundaries contained by the slicing area, and then inserting the new items that exceed the slice boundary. So we have some methods for the list and tuple implementation. The first one is the insert method. If you want to add some value to a specific location in your list, it's going to shift the remaining items to the end of the list. For instance, I want to insert 15 at location 2. So this is location 0, 1, and 2. It's going to insert 15 at this location and shift 5, 6, and 7 to the end of the list. Let's run this code first. There are some other codes that are uncommented at the end. Okay, now let's run it once again. Okay, now this is my initial list. Output without any modification. I have inserted 15 at location 2 and shifted the remaining items to the end of the list without overwriting the existing items. You can also use the append method, which inserts items to the end of the list rather than at some specific location. What happens if you want to insert some item beyond the length of the list. So we have the length as 5. I want to insert something at position 5 first. And let's run this. It can insert at location 5. Let's try inserting something at location 6, which is larger than the current size of our list. It's going to again insert it to the end of the list. So if it is the provided index is larger than the length of the list, so it's going to simply append it to the end of the list, no matter how large you specify this index. If you want to assign the value with a negative index, it inserts it to the position 1 before the last item. You can simply do that as well. So what happened is the length was 5. 5 minus 1 is 4. So my new item has been inserted to index 4. And the item in index 4 has been shifted to the end of the list. For you, it's the end of the list like this. For me, it's like this. Okay, so if you use the append method, let's comment this insert part. And let's use the append. So what happens is it's going to just simply insert or add the provided value to the end of the list. This is how append works. But there's a catch in this case. If you keep inserting or appending elements to a list inside a for loop, that loop might not end. Okay, if you have such a code like this, where you simply keep inserting the items to your list. Initially, our list has a single entry, which is 1. So the loop starts iterating over the values contained in the list. So x becomes 1. And then inside the loop, somehow we end up appending to the list. And the loop is going to complete at this point, go back to the check, and it sees that it has consumed this element, but there's a new element in the list. It's going to assign 1 to x, and the same operation is going to take place. And then it's going to go back to the conditional, go back to the control flow, to the for loop. And then it's going to encounter that it has consumed this one, but there's a new one. So this keeps on and on forever, if this is your case. So you should be careful. It doesn't assume that the initial version of this list was containing only single entry, and I'm going to process it, and the loop is going to be over. It just keeps checking whether there are new items inserted at this current state of the list. So in some other programming languages, we encounter that only those were in the list or array in that state were being processed, or the list was not allowed to be modified inside a for loop. So this is not the case in Python. You can modify the list you are iterating over, and you might be adding, removing two from the list that you are currently iterating. Just this is an exceptional case for you. Keep in mind that your loops might not end because of this phenomenon. Okay. You can also extend your lists using the extend method, which is simply going to append another list to the end of an existing list. And the list is going to be modified, by the way. It's not going to return a new list. It's going to simply add all those items to the end of the existing list. In this case, we have the temp list consisting of 5 elements, and we have defined a set using the curly braces, and we can extend our initial list using this set, and also we can extend our list with a slice of a tuple. So this is the temp tuple, is a tuple, and this slice is going to start from here and here. So there are going to be 2 items that we receive from the tuple. Also, we can use a slice from the other list, or we can use the entire list as we did in the temp set example. So if you run this code here again, let's have the extend code. Okay. Oops, I did something wrong. Let me go back. Okay, instead of having these, let's comment this part out. One, two, three comments. Extend. Comment this part. And run the code. So we have extended our initial list, which was 1, 3, 5, 6, and 7, with all items from the set, and with partial items, a slice from the tuple, and another slice from the list. And after that, I have modified my example in the earlier recording. So you can see it here that I have also appended the list, the second list entirely at the back of the original list. So my list, my temp list has been modified. It contains all those elements that are extending, that are used to append to the end of the list. So it's not a new list, but my list in the computer memory has been extended with new items. So they are all appended into the list that is inside the same location. Yet the location, the amount of space it consumes, it is longer, but the initial position of the list does not change. You can also use the plus operator to merge 2 lists or tuples together, but the result is going to be a new list. It's not going to be modifying the colors one. Okay, it's going to merge these two. It's going to merge these 2 lists together, and a new list is going to be generated using the values from both lists. And if you print these, or if you want to use those values from your new list in a for loop maybe, or a function implementation. Okay, now it's okay. So let's first run this code, which is colors 1, colors 2. As you see, although I execute the merge statement before the print, both colors 1 and colors 2 are intact. As you see, it starts with black and it ends with pink. Similarly, colors 2 starts with red and ends with cyan. However, the merge list is a new list that appended the second list to the first list, without modifying these ones. So extend, append, insert modifies that list. That modifies the list that those methods are being operated on. However, the plus operator simply generates a new list. So you can keep your original versions of those lists. So if we convert them to tuples instead of lists, and apply the plus operator, it's still going to generate a new tuple from the existing tuples, but you cannot apply extend or insert, append methods to tuples because tuples cannot be modified. You can also remove items from a list using the remove method. It's going to remove the number 3 from your list. It's not going to remove the item at position 3. It's going to remove 3 from that list. It's going to remove the first occurrence of that 3 or that value. So if we move on with our example, I have 3 to be removed. And let's keep pop as well. We're going to discuss pop and delete together. So let's leave it like this. Okay, the first example is for removing 3 from my list. Let me have the yellow string, and let me have another yellow string. So if I want to remove yellow as well, I have to simply specify it as a value to my remove method. So this was the last version. Copy, paste. So let's print the original version of the list. It contains 3 yellow and yellow. When I remove 3, it's not going to go and count 0, 1, 2, 3. It's not going to remove 6. It's going to find this 3 if it is present in your list, and it's going to remove that item from your list in the memory. Okay, it's going to modify the list in your memory, removing 3 and continue with 5, 6, and the second 3 is not modified, and 7, and it's also going to remove yellow with the second remove statement and leave the other yellow in place. So my final version of the list is that I have removed this 3 and I have removed this yellow from my list, and I'm left with another 3, which was the second, and the other yellow, which was also the second instance of yellow. So if you want to remove all of them from your list, you might need to establish a for loop or something like that and remove all of them by checking whether the value is still contained in your list. There might be other functions to remove all occurrences of the specific item from a list. For in or you might simply establish a while loop, while 3 in temp, simply temp.remove 3, and it's going to remove all 3's from your list, no matter how many you have. 3, 3, 3, and if you run this code, you're going to see that there are no longer 3's. in your list. So while works just like the if. When you use the in operator in a while statement, it's going to check whether something is inside this temp value. But in case of for something in temp, the in operator is going to iterate over all those items in the temp container, which might be a list, whatever, a list, a tuple, maybe a set, dictionary. So it's going to iterate over all those values and assign them one by one to this loop variable. But in case of while and if, the in operator simply checks whether this thing is present in the container, which might be a string or a list or a tuple, and so on. So the use of the behavior of while is very similar to if, and the only difference is that it repeats itself as long as that condition is true. And the next example is that we have a pop method which is going to remove an item at a certain index. So it's not going to pop the 3 from the list, but it's going to go and find the item at index 3, which is 6, and remove it from your list. And it's going to return the popped value. So it's going to first find that element, which is 6. It's going to remove 6 and return you the value popped out of your list. And you might want to use that information at the later steps of your program. So the difference between remove and pop is remove receives the value of an item to be removed. Pop receives the index of an item to be removed. And we also have the del keyword, which you can use to remove items similar to pop. So if you write it like this, delete 3 from temp, it's going to go and find the item at position 3, which is this one. It's going to remove that from the list, modifying the original version of your list in memory, and it's going to output this. You can also delete the entire variable, the temp variable, and after that you cannot access to that variable because it becomes undefined. So let's run this first, and I have this example. I have removed 6, so it was pop. Let me just comment the earlier steps so that we can go line by line. Okay, let's run this now. I have this list of 6 items. I first delete the item at index 3, which is 6, as in this line. And then I have another list. Populated with the values 1, 1 and 45. Also a reference to the current temp. So I had my temp list, which contained 1, 3, 5, 3, and 7. Okay. But my new list, which is the bulk list, contains the values 1, 45, and a reference, address reference to this existing list. So it's keeping in mind that it's going to use these values. So there's an active reference to this list. Even though I delete the temp variable altogether, it doesn't delete the values contained in this memory space, because they are going to be accessed by this new pointer inside the bulk list. So this is another example to the pass by reference situation. And then whenever you need to access the second item in the bulk list, which is the which is the latest version of the temp list, it's going to simply output these values for you. You can also make a new reference. So I haven't output this. You can also reassign the temp variable, print temp. Okay, but this temp variable is a different one than the earlier temp variable. Okay, it's not stored in the same location. It's hardly possible that it's going to be at the same location, but it's an independent variable which is other than the earlier temp variable, just a new one with the same name, but they have no connection at all. So this is not going to be pointing to the list which was assigned to the variable with the same name automatically. But if you want to keep track of that data, you can simply use this statement to assign that string, that list stored in that specific location. It's just a pass by reference operation. And now we have a new variable pointing to the list stored, referenced by this bulk list, referenced by the second element of the bulk list container. And we also have the clear method, which simply removes all items in a list, but it doesn't remove the list itself. So the list was here. It contained 1, 3, and other items. When we call clear, all these items are removed from the list, but the list itself is preserved at the same location as it was before. So all the references from other variables, other lists, other containers are preserved. They are not modified. But whenever they want to access the elements inside the list, they are not going to find anything. But the access operation is not going to fail. It's not going to raise any errors. So clear is different than del. Del simply removes that variable pointing to something or not pointing to nothing at all, but it's just removed from the interpreter's memory or access tree. Next we have the sorting concept. As we all know that lists and tuples preserve the order of elements that they contain, as long as the items are not reordered or rearranged with respect to their values or other ordering principle. Sorting, on the other hand, is rearranging the locations of those items based on their properties, such as their magnitude, their lexicographic ordering, or if you are dealing with complex types or custom entity types, you might specify the ordering principle, not only with respect to the magnitude they contain, but the time of arrival or creation time, or other properties such as sorting students with respect to their GPA value, with respect to their ID number, or their department. So sorting is the concept of reordering items in a container, which is usually a list, based on their specific features. So basic sorting, using the sort method in Python, simply orders the items in a list based on their magnitude or based on their value or quantity, if you may. So we have this example using the sort method of lists. Let me just reorganize my code because I have recorded this earlier, modifying all the examples. So this is a second recording. And my original list is 1, 2.33, etc. So it's not sorted. The order is preserved. So unless you modify your items in the list, the item at position 0 is always going to be 1. The item at position 2 is always going to be 3. Okay. The ordering is always preserved. However, if you apply the sort method to your list, it's going to rearrange their positions from smallest to greatest. So this is the output of the first sort operation. Let's print the original version of the list first. Let's copy this line and print the original version, and then we apply the sort on this. So this is the original version. This is the sorted version. And the final list is the reverse sorted version of this list, where we specify the reverse parameter to be true to the sort method. It simply sorts the items in the list in descending order instead of ascending or increasing order. It uses the decreasing order of elements, where the greatest item is located at index 0, and the others simply follow that greatest number, and the last item in the list is the smallest number if we are working on numeric lists. If we are dealing with string lists, it's going to be using the dictionary ordering or lexicographic ordering of items, which we will cover soon. There's also the reverse method, which is not the same as sorting with the reverse parameter set to true. Reverse method simply uses the initial ordering and reverses the order of elements. So it doesn't keep track of the magnitude of the items the list is containing, but instead it's taking the last item to the first position and the one before the last to the second position, and so on. So it's simply moving them in locations in the reverse order. It doesn't look at, or it doesn't check the magnitude of the items, so it doesn't apply the sorting. Instead, it just reverses their positions in the list. So the last element becomes the first element, and the first element becomes the last element, regardless of their magnitude. So reverse function is not sorting, but instead it's reorganizing the elements in the original list. If we have a list of strings, and if we want to, let's have another string here, which is AA. Okay, it's not a color, but just to show you the lexicographic ordering. And if we run this code, it's going to first use the, and let's also have a single A as a string. So this is how lexicographic ordering works. So it's going to place A as the first element in the sorted list, followed by the AA, and then the azure color, followed by black, blue, orange, pink, ruby, and violet. So this is how it works on string lists when you run the sort function, sort method. Okay. But if you want to run sort on a list of numbers and strings, so this is a mixed list that contains items, or you might also have a Boolean value as well. So if you want to sort this list, it's going to raise an error because it says I cannot compare strings to numbers or Boolean values to integers, etc. So if you want to run the sort method on your list, all the items in the list have to be of the same type, or they should be comparable against one another. By default, we would expect that the sort algorithm to treat numbers to appear before strings, as in some lexicographic ordering algorithms. But Python does not follow that convention. It just simply expects all those items in this list to be of the same kind, such as strings only or numbers only. But it can simply sort numeric lists containing integers and floating point numbers at the same time, because they are comparable using this less than operator. Just keep in mind that you cannot compare these two, or use the sort operation, sort function, sort method, whichever you like, on mixed lists. If you need to sort tuples, which you cannot directly run the sort algorithm, you can convert that tuple to a list using the list constructor, as in this case. And then you can sort that list and generate another tuple from the sorted list, but they will not be the same elements. So let's just convert this to a tuple first. Instead of a list, I use the regular pair of parentheses, and I cannot run the sort method. Let's see. Sort has no attribute, tuple has no attribute as sort, so you cannot call a sort method on a tuple, but you can generate a list. Colors list is list constructor receiving a tuple as the argument. Now I have a list which I can sort. Okay, think of this as you have a memory location. There is this memory location. You have the colors tuple in your memory. Now you are generating a list using these colors, so it's a new memory location, colors list, constructed using these. These two are independent from each other. The list uses the values contained in the colors tuple, and then from there we sort the colors list. Now I can reassign colors. Let's make it colors2 equals to be a tuple from the sorted colors list. Now in this case, I have accidentally deleted my screen. In this case, I had my colors, which was the tuple colors list, which I sorted, and it was a different instance from this colors at an independent location. And when I run this statement, I generate a new tuple from this list. Okay, this one was used by this one, and then this is used by that one. This is the colors2 tuple, which is the sorted version of the colors tuple, but they are independent from each other. They have no relation whatsoever. If you had references to this colors from some other location, they are not linked to this new location. So they have no connection at all. And if you also reassign colors instead of colors2, okay, although they have the same although they had the same name, so it was initially pointing to this location. When you make this reassignment, the colors is now referencing to the new location, so as this one, because they are the same variable. It's no longer pointing to the older location. It is possibly present in the memory. It might be referred by some other variable, some other container, etc. But the colors variable itself is now pointing to the new location. It has again no connection to the older version of this one. But this doesn't mean that if you had some list, my list, containing the colors and other things, okay, so this doesn't mean that my list is now going to go and point to this one. This is not true. The colors in my earlier list were pointing to this location with black, azure, ruby, orange, in that order. But whenever I reassign these colors to the sorted version, my other list is not going to go and automatically point to this location. There is no such thing as pointing to this location automatically, because this assignment is a totally new assignment. So the variable is not going to be automatically mapped to the new memory location because of its name. So these references are very important. We can experiment this in, let's say, let's have this other list. My list is consisting of colors and some other information, other info. Okay, now if I print my list, I am going to see something, and then I'm going to reprint that list, my list, at the end of the program. Let's run this. So I initially had this list containing my original tuple. At the end, I still have the same thing, which was being pointed by my list in the memory. So this was pointing to the same location here as colors. which started with black, A, sorry, AA, etc. They are all pointing to the same location. However, I modified this one. It's now pointing to some other location, but my reference is still intact. This my list container is still pointing to the older place, older location in the memory. Whenever I reprint it after all those assignments and modifications and sorting operations, it's still going to point to the same location without any modification. So unless you modify your list to point to the new location, which you can do like in this example, so you modified the colors. Now you can my list 0 equals colors. If you do this, let's make a before and after version of it. Let's print it first and then reassign the first element in my list. Now we see that it's pointing to the new location because we have modified the item at index 0 with the new colors that we obtained from the color list. So it's not going to automatically go and do it itself, not in this line, but when we reassign that first element, which was initially colors with the older version, making a reassignment to the modified version is simply going to go and refer to the new location, to the location of the new sorted tuple, sorted list and the generated tuple. There are more operations that can be performed on lists and tuples. So first of all, we can simply assign a list to multiple variables. Whenever we sort the first, sort based on the first variable, the other variable referring to that same location is also going to have the same effect, because colors is pointing to this location. Now when we assign colors temp to the existing variable, it's also going to point to the same location because of the pass by reference principle. And when we sort colors, as the second variable is also pointing to the same location, it's also going to be sorted. So there aren't any copies of the same list, but the two are pointing to the same instance. Let's execute it before we move on. So we have this list of black, azure, ruby, orange. Let's print it if you like. Print colors. And we sort the colors. Or if you like, we can print the colors temp first, so that it is not a copy of the sorted. Print colors temp. So we first output the colors temp and we sort our list using the first variable. Black, azure, ruby, orange, and when we sort the first variable, it becomes azure, black, blue, and when we print the second variable, it simply prints out sorted version. So let's move on with the examples. Okay, we have this is the original version of the list. So we have the copy operation, copy method for a list. Colors copy, which is like this. Colors copy. Okay. As I told you earlier, I have already modified the examples in an earlier recording, which unfortunately failed. And we have this colors tuple, the list, sorry, and we make a copy of this list, which means that we already had a list in memory. Okay, this is our memory, conceptual memory. So my colors were at this location. As soon as I execute the copy command on my colors list, it's going to take the contents of this memory area and copy them to a new location, black, etc. So it ends with pink. Okay, so they both contain the same primitive types in different memory locations. Now colors temp is referring to this new location. Colors is still referring to the earlier location. So these are two distinct lists which can be present at multiple times at different locations, because we might perform different operations on different lists, although they contain the same items in different ordering maybe. This is allowed for lists, but it's not allowed for tuples. Tuples in principle are stored at a single location as long as it contains the same sequence of elements. And in the example, we have this copy function. So when we sort our colors, let's print this colors first, colors, and then let's print the colors temp, and let's sort our colors, colors.sort, and let's reprint our colors temp, which was the copy. Now we can see that it's not altered by any means. Let's print a sequence of dashes for this example, so we can differentiate our contents. Let's run this. Run. It says you have too much comments. Okay. Run. So I had this. Let's move it to the end. Remove the one from the middle. Okay, I think it's all clear. It's not. String object has no attribute pop. I'm going to comment this because this was another example which I'm going to show you very soon. Okay, now let's run this. Okay, I had my initial list. I had my initial list. Colors, black, azure, ruby. Okay. Let me print colors here as well, which is sorted now. Okay. Now we have, this was the colors. This was a copy, not an assignment or pass by reference, but an individual copy with all items stored at a different location in memory. Now this third one is, this was the second one. The third one is pointing to the sorted colors. Okay, this is colors. This is colors temp. So when we apply the sort operation on colors, it is still in the same memory location, but the elements are rearranged on their positions. So they are moved from one place to another place, but the list is still at the same location. It can be accessed using the same memory address, but the order of elements are modified. But colors temp is an individual copy, a different copy, so it's not affected by the sort operation. It was residing at some other location in the memory. So making a copy of the list means that you are not going to have the same reference as the initial list which you made the copy from. However, if I make my list to contain another list which is not a primitive type, what happens is in memory now we have this structure. Let me try to draw it in a better way. So my first list is containing the values black, Azure, and so on. And there's a reference, a list reference. This is a memory address, okay? Address reference to another list in my memory which contains blue, violet, and pink. So this is an individual list. I have a reference to this list in the memory, and when I make a copy of this colors list, it's going to reserve space for colors temp, which contains black, Azure, etc., and that reference again pointing to the same location as the initial one. So this internal list is not replicated by the copy function. Okay, we make a copy of each primitive type from one place to the other place. Okay, all these strings, numbers, etc., are Boolean values, etc., are copied. But when it comes to a complex type contained in my list, such as a list or a tuple or any other structure, compound structure, complex structure, it's not going to be copied, but the reference is going to be replicated, pointing to the same location. Now what happens is, I have my code. Let me remove these parts. We sorted the colors, we made a copy. I don't think we can sort the list containing, so it's not supported between list and str, so the sort function is no longer applicable to my example because I have strings and a list contained in the same list, so it cannot compare a list against all these strings to decide which one comes first. So I will not be able to use the sort function, but I am going to simply show you what happens if I want to pop the elements from one variable. Okay, so I'm going to try to pop the element at index 1, which is Azure. Okay, and then I'm going to retrieve the third item from my list, which is going to be 0. This one is going to be popped, so this is going to be 1, 2. So this is the third element in my list, and I'm going to pop the element 1, which is this one. Now 0, 1, 2. I'm going to pop violet from this smaller list or internal list, and then I'm going to both output colors and colors temp. So all operations are performed on colors, and the effect is going to be reflected to colors temp, although it was a copy of the colors in the first place. So let's execute it without clearing the screen. Okay, now I have my colors output as black, ruby, orange, blue, and pink. But colors temp has Azure not removed because it's a primitive type and it was replicated in the memory to another location. Okay. But my common list, common entity between the two lists has been modified by this operation, retrieve the third item from the list, which is actually the internal list containing blue, violet, and pink. And removing violet, pop 1. This is the first index, 0, 1, 2. So 0, first and second. The first element, the second element, if you like it. Removing this has an immediate effect of the other list, the colors temp, the clone list, to be accessing the modified list as well. So it has black, azure, ruby, and orange in its memory space. Black. Although azure was removed from the other list here, it is not removed from the copy. But whenever you remove something from a common area which is referred by its address or passed by reference, the effect is immediately visible when you look at the clone, because the information was not stored in that second list. It doesn't make a copy of complex types in this copy operation does not make copies of the complex types contained in the initial list, such as the internal list here. So this is not copied. These are all copied to the new list, but this is passed by reference. Okay, now you can also copy lists using the list constructor. Okay, it has a similar effect to the copy function. When you use it, similarly, if you have complex types, it's going to be referencing by value. It's not going to replicate the internal complex types. You can generate lists from tuples, other lists, dictionaries, sets, etc. But there's this feature of the sets which prevents the ordering to be preserved. So what I mean is, when you insert items to a set, the set does not guarantee that they are going to be ordered in the same manner. So I have this yellow, white, magenta, this line. So this line is simply a list generated from a set, yellow, white, and magenta. So when I re-execute this code, you're going to see that the order has changed. Although I haven't modified my code, it became white, yellow, and magenta. So if you keep running this code over and over, you may see other orderings. Let's run it once again. Yellow, magenta. Now I had yellow, white, magenta, and now I have previously I had white, yellow, magenta. Now I have yellow, magenta, and white. So the order of items is not preserved by the set. So you cannot rely on that ordering, that when you generate lists from the sets, you cannot expect them to appear as you inserted them, as in the order you inserted them. So set doesn't give you any specific ordering. If you need them to be ordered in a specific way, based on a specific algorithm, so you might prefer in your algorithm that hot colors to appear before cold colors instead of their naming. You might write such a function to generate the ordering accordingly. But in this case, if you sort them as strings, it's going to appear that magenta becomes before. Where is my code? Let's sort it. So if I want to sort my colors, print colors temp dot sort. If I want the sorted version of my colors, it's going to appear as which line? Red, purple, cyan, yellow. Print colors temp dot sort colors. I have generated this. It says none because it returns none. Okay, I have to. So this function returns nothing. I have to do it outside the print. So the return value of sort is none because it's making the changes in memory. Now if I print the sorted version of this colors temp, it's going to display that magenta becomes before white, becomes before yellow. So this is the sorted version based on their string values, the color string values. You can generate lists from other lists, tuples, sets, as you have seen. When you generate lists from dictionary, when you generate lists from dictionaries, you're going to see that the list will only contain the key part of the dictionary. Okay, it's going to ignore the values and generate your list using the keys of that dictionary. They might appear unordered as well, similar to sets, because dictionary is a special form of sets. So in this case, we had yellow, blue. If we run it for larger dictionaries, maybe it might return other values. So it's insisting on showing the insertion order, but when you make some operations on this colors dictionary at later steps, how it resides in memory is something like this. So you have your dictionary components. Let's say yellow is here, blue is here with their counterparts or values. So when you make an insertion, let's say you inserted red, it's going to appear at some other memory location. So these are going to be linked to one another using some linking algorithm. When you want to generate list from these values. The order may change, may depend on the algorithm that's generating the list from this. So it might be using the accessing order or the of the keys, which one it was accessed before. Uh, Also depending on the implementation of your dictionary, which might be a tree implementation, okay, or a linked list implementation where items are pointing to one another based on a specific algorithm. The collection of these items gives you the ordering of generating the list. So for sets and dictionaries, you cannot rely on the insertion order because you might add something, remove something from those items. So the order is not guaranteed for either sets or dictionaries. So you should not think that whenever we generate a list from this set, it's always going to be yellow, white, and magenta. Most probably it's not going to be that way, considering the fact that the sets might contain hundreds and thousands of items. Similarly, colors dictionary might also contain such large amounts of data. You cannot expect them to provide the same ordering you have in your same ordering you introduced your items to the dictionary or the set. Okay. And also you can generate tuples from lists, sets, and dictionaries, as in the case of lists in this example. And also you can replicate your tuples using the star operator. Just as in strings, it's going to simply generate a replication of the same tuple. So you can use the plus operator as we have shown in the earlier slide. Also, you can generate a this is not a tuple, although it contains the word tuple. It's going to be a list because we are adding two lists back to back. And then from there we can generate another tuple using the same operation or this variable, which is a list. So the tuple constructor is simply going to return you a tuple generated in the memory, which cannot be modified on its own unless you convert it to a list. If you convert it to list and back to a tuple, it's going to be a new instance of the tuple with no relation to the earlier version of that tuple. Okay, so let's move on to this replication. Okay, let's do them both together. Run. I have this tuple consisting of 1, 3, and 5. When I multiply the tuple with 3, it's not going to multiply those individual values by 3 as in matrix multiplication, but instead it's going to simply replicate the tuple 3 times in the same order and generate a new tuple from this operation. It's not going to modify that original tuple, but a new tuple is constructed using the original or the earlier tuple. And we have the count method for finding out how many occurrences are present in a specific tuple or list of the given argument. So if I want to count the number of 11s in my list, it's going to return 2, as in this line. And if I want to know how many 13s are in my list, it's going to count all occurrences of 13, which is 1. Similarly for 15, which is also 1. But if I want to look up the index of the first occurrence of 11, it's going to return 0, although it's also present in location 4. Okay, 1, 2, 3, 4. It's only going to return 0 as the first occurrence of this argument here, provided to the index method. I think this wraps up the section. Okay, you can use the index method on both of them. Let's see if something that is not present in our list is asked. So we don't have 17 in our tuple, sorry, tuple, not list. It's going to return that X is not in tuple or list. So you might receive this value error, or you might simply try it for the count as well. Let's count. It's going to return 0. Just ignore this part for the time being, and let's try count for 17. So there are 0 17s in my tuple, so it's not going to fail. But when you work with index, it's going to raise an error exception that you should handle, that tuple X, the value error, it's not present in your tuple. So if you're checking whether something is present in your list or not, in your tuple or not, you should use the try except block, except print, so that your program does not crash. The value is not present in the tuple. So let's run this. So it says the value is not present in the tuple. If I the rest of the program, what happens is, if I don't write it in a try except block, it's going to halt my program. So the rest of the program is executed here. So if I ignore this, if I don't write my code, that is probably going to generate an exception within a try except block. It's going to prevent this line of code to be executed. So the program crashes at this point with this error. So I didn't handle it, and it's not going to execute the rest of my program. So it's a very, very good practice to identify potential exceptions that might arouse from some statement, which is the case in the index function, index method, that it raises a value error where the value is not in the tuple. It's not handled. It doesn't return something like -1, because actually in Python -1 is maybe a legitimate index value when you are working with tuples or lists. So it starts from the end of the string, end of the list. So if you give negative indexes, it's going to start from the end of this list, both in tuples and lists. So returning some negative value does not solve our problem. So returning -1, 0, 1, 2, -2, these are all legitimate index values. So if we ask at which index 17 is in this tuple, it shouldn't return a negative value, because we would treat it as a valid index. Instead, it raises an error. So this is in the description of the index function, which you should all look up when you are using some functions from a library. So it's definitely going to raise an error if you don't write it in between the try except block. If you do this like this, and then you're going to be able to recover from that error. Maybe you're going to inform the user that this value is not present, so you might insert it on your own. You might terminate your program. You might return some value, some default value to the user, whatever you need to do. But when you fall into the trap of an error which is not handled by a try except block, your program is going to crash and it's not going to execute the remaining part of your code.